Hi everyone. In this video we'll see another proof using totally different techniques than we used last time. Namely, we will use induction and we will also do a small contradiction proof. So the lemma that we will try to prove is the following. So when G is a tree, so remember a tree is a graph with no cycles, and we have at least one vertex, then so the number of vertices is equal to the number of edges plus 1. So let's first take a look at this example tree that I drew here. So you can easily see that there are no cycles here, so it's indeed a tree. So let's first count the vertices here. So we have 1, 2, 3, 4, 5, 6, 7, 8. And the number of edges is 1, 2, 3, 4, 5, 6, 7. So for this example, we indeed have that the number of vertices is the number of edges plus 1. But of course, this is not a proof. We would have to draw all possible trees to prove the statement. So instead, we will use a proof by induction. And in induction, you usually use this when the smaller problems are related to larger problems in some way. So we always start by writing that we will prove this by induction. So we will prove the lemma by induction. And then we need one more thing. So we need to state what we do induction on. So in this case, we will use the number of vertices of the graph. So by induction on, so the size of this set. And then the first step in induction is always to look at the very smallest case. So we call this the base case. So the smallest number of vertices that we can think of is 1 because we need to have at least one vertex, the statement says. So that is just a graph with only one vertex. We can have no edges because they don't have anywhere to go so self loops were not allowed. So this is not allowed, so we only have one vertex. So the size of the vertex set is 1 and the size of the edge set is 0. So indeed, the statement holds for this very small case. So that's enough for the base case. Then we go to the induction step. So for this step, we will assume that the statement holds up to some size, and then we will look at one step bigger. So we assume the lemma holds for any size of the vertex set smaller or equal to k. And then we will look at one step larger. So now let's look at a tree G. So be a tree with k plus 1. So the next step, vertices. And then we somehow want to make a smaller graph such that we can use this statement for the smaller graph. So the first claim that I make is that G has a degree 1 vertex. So let's take a look at this example. Here we have a lot of degree 1 vertices, so they only have one edge attached to them. So all of these vertices are degree 1. But we want to show that this is true in general, that we can always find a vertex of degree 1. So we'll prove the claim here. And we will prove this by contradiction. So we first assume that the opposite of the claim is true, and then we will arrive at the contradiction at some point. So assume that this graph G has no degree 1 vertex. So apparently all the degrees are at least 2. Because we have a tree, so we already know that it's connected, so we cannot have any degree 0 vertices. So then we will create a walk through the graph. So we start a walk at some vertex, at a vertex, and so we start a walk at some vertex of the graph, then we will move to another vertex, and then we can continue to the next one, etc. And apparently we have no degree 1 vertices, so we will never hit a dead end. So if we continue like this, then at some point we know that we have to run into one of the things that we have seen before already, because we can always continue. But that actually forms a cycle. And we said we had no cycles. So let's try to write this down a bit more formally. So we start a walk at a vertex. Then we can always continue. So we can always continue the walk. Because each vertex has degree at least 2. So greater or equal to 2. And so this is important because this G is finite. We run into something that we have seen before. And as we saw, this implies that there is a cycle in the graph. Oh, cycle, sorry. And that is a contradiction, because there were not supposed to be any cycles. And to denote a contradiction, we use this sort of Harry Potter arrow that we see here. So that's the proof of our claim. Now let's try to apply the claim in our proof for this lemma. So we know that the graph has a degree 1 vertex. And what we are going to do is that we are going to remove this vertex. So let's say in this example here, we remove this vertex, and so also the edge that is attached to it. And then we get a smaller graph where we can use our induction hypothesis. So let's say we call this vertex V, the degree 1 vertex. Then we consider the following graph. So this graph G prime, which is, so the original vertex set minus this vertex V. And this is a set. So we remove the set that only contains the vertex V. And then let's say the edge that is attached to it is called E. Then remove that one from the edge set. So this graph has only k vertices. So we can use this statement for this graph. So we know that this phi prime, so the size of phi prime is equal to the size of E prime plus 1. And there are two more things we know, namely that the original size of V, so that's equal to the size of the V prime plus 1, because we removed one vertex. And similarly for the edge set, we also have that this is the size of the new edge set plus 1. So then we will try to write down this statement for graph G, and then use these formulas to get to the final proof. So what holds for the edge set of the vertex set, of G? So that is equal to the V prime plus 1. For V prime, we can use this statement here. So this is equal to E prime plus 1, and we have this plus 1 here as well. And then we know that this is equal to the number of edges E from this statement here. So this is actually equal to the size of E plus 1. And this is exactly our statement that we want to prove. We have the size of the vertex set on the left here, and the size of the edge set on the right. So now we have actually proven our statement. So in the next video, we'll see another example of induction, because I feel like it's a bit difficult to get at the start. But hopefully this helps you to understand the principle of induction.